So game plan is, I was pretty much done with 7.3. So I'm going to start 7.4. I probably won't finish it. I don't need to finish it. I think I've sort of caught up. Okay. And then second half, I'll be giving you a quiz. It's the quiz that I was going to give you last week. So it'll be on section 1 and 2, integration by parts and some substitutions. Okay. And so where are we? We are up to roughly here. Okay, so today we're doing something called partial fractions. Partial fractions 7.4. So let me show you something like that. So we're going to have rational functions. Rational means polynomial divided by a polynomial. Okay. The technique is called partial fractions. So how do I integrate weird looking stuff like that? Okay. Now the first thing we want to review is a concept called polynomial long division. You remember doing long division, something like this? You don't have to look at this in detail, but if the degree of the numerator is bigger than the degree of the denominator, right, like this says x cubed plus x divided by x minus 1, you can do long division and make it look like this, right? We'll be doing some problems like that. And then this becomes fairly straightforward. You have this, that's easy, that's easy, that's easy. Anytime you have something like that, that's going to be a natural log, right? To integrate that, that's 2 times 1 over x minus 1. 2 times ln absolute value of x minus 1 plus c. Right? So there's a certain class of problems like that. But the main idea behind partial fractions is something more difficult. Okay, and we'll look at some problems involving that. All right, so here we go. So yeah, I was done with just about everything I needed to show you from 7.3. Okay, so I think I did enough of those, so you try to do the rest. And I'll get started with 7.4, but probably not finish it. Okay. Again, when I say 7.4, you know that my problems may not match yours. It's always like that, so be ready for that possibility. Okay, first thing I'm going to show you is something like number 7. Which is actually hopefully fairly straightforward. X to the 4th over x minus 1. Okay, now, you could do polynomial long division for that, but I think there's something a little bit better. What I want to do is get this down to a polynomial plus some remainder that has an x minus 1 in the bottom. Okay. The trick that I did here was to subtract 1 and add 1. And the reason why I want to do that is because I know how to factor this. And if I factor this the right way, I can eventually cancel out that x minus 1 in the bottom. Okay. So we're trying to integrate fractions, rational expressions. So I'm going to go x to the 4th minus 1 plus 1 over x minus 1. And then I split it into 2 like this. Okay. This is easy to integrate. That's your natural log. Like I know right away, it's going to be ln absolute x minus 1, right? This thing here is going to be some factorization and cancellation and stuff like that, right? So it's not going to be so bad after all. So how do you factor x to the 4th minus 1? It's x squared plus 1, x squared minus 1. Just leave this alone. This is already as good as it's going to get. All right, so we'll just leave that alone. Oops, let me check something here real quickly. Yeah. All right, so I have that now. Now I can change x squared minus 1 into x plus 1, x minus 1. And then these guys cancel out. So I have x squared plus 1 times x plus 1. I still have this thing here, but that doesn't bother me. I will distribute. So FOIL this out, right? That times that, that times that, that times that, that times that. So x squared times x is x cubed. X squared times 1 is x squared. 1 times x is x, and 1 times 1 is 1. Okay. Now I've taken the original problem. Look at my original problem. X to the 4th over x minus 1. I made it look like this. And the reason why you want to do that is it's integrable. I know how to integrate this now. Okay, so now it's easy. X to the 4th over 4, x cubed over 3, x squared over 2 plus x. And to integrate 1 over x minus 1, that's ln, absolute value of x minus 1 plus a constant. And that's all you have to do for that. Okay. All right, so now for actual partial fraction problems. Okay, so in order to do that, I have to make this disappear for a moment. So I'm going a little bit out of sequence here. I'm going to show you something else. So let's look at this. Partial fractions. So I'm taking a big time out. Taking a time out and go over the concept of partial fractions. All right, let's think back to our Algebra 1. 2 over x minus 1 minus 1 over x plus 2. How do you combine in algebra, right? So you know what to do. You need a common denominator. So when it's like this side needs that, and that side needs that, right? So this side you multiply by x plus 2 over x plus 2, whatever you had in the denominator there. And this side you multiply by x minus 1 over x minus 1. Right? So that way you have a common denominator. Agreed? So I have a common denominator, just work on the top. So 2 times x plus 2 is 2x plus 4. And then minus 1 times x minus 1. Negative 1 times that, you just change the sign, so negative x plus 1. And now you have x plus 5 over x plus 2, x minus 1. Okay, so no big deal. You've done many of these problems in your algebra class. Okay. What you may not have done is to go backwards. Suppose you started off with x plus 5 over x plus 2, x minus 1. Can you bring it back into this form? In other words, sum a over x plus 2 plus b over x minus 1. Now, of course, in this particular case, we're kind of cheating. We already know what the answer is supposed to be, right? We just peek up here. That should be a 2, and that should be a negative 1. But suppose you didn't know that. Okay, so suppose this wasn't there, and you started off with x plus 5. If you want to know what that is, I'm sneaking in a 1. 1x plus 5 over x plus 2, x minus 1. Okay, most of us maybe didn't do this before. Okay, but I'll just mention why do we want to do that. If you can get it to look like this, then it's an easy integration. Constant over x plus 2 plus constant over x minus 1. They're both just going to be some natural log. So let's pretend this came out to be, I don't know, 7, and this was negative 4. Then you just go 7 ln absolute that minus 4 ln absolute that. Okay, so how do we go back and find a and b? Right. So again, I'm guessing everybody's very good at this. Right. How do you make that look like that? Get your common denominator, right? Multiply by x plus 2, x plus 2. Multiply this by x minus 1, x minus 1, right? And now that you have a common denominator, just combine all the top and you have this. But how do we go backwards, right? How do we start off with this and get back to here? So here's the technique of partial fractions. Just start off with a over x plus 2, b over x minus 1. Okay, so right now you don't know a or b. Just go ahead and get your common denominator, which really means do the same thing over here. The only difference is that over here you knew there was a 2 and a negative 1. Here you don't know the value of a or b, but just do the same thing. So multiply this side by x minus 1 over x minus 1, right? And multiply this side by x plus 2 over x plus 2. So now you have your common denominator. Work out the top. So ax minus a plus bx plus 2b. Right? Common denominator, x plus 2, x minus 1. Ax minus a plus bx plus 2b. Now, I'm going to group them together. I'm going to combine the x's. So I'm going to lump these two together. And then the constants that don't have an x, put them together. So notice how I go a plus b parentheses x, which is that and that combined. And then negative a plus 2b. There it is, right? So a plus b x plus parentheses negative a plus 2b divided by x plus 2x minus 1. And what's my goal? I want it to equal x plus 5, or 1x plus 5 over x plus 2, x minus 1. Okay, so how can I get this fraction to match this fraction? Well, the bottom's already the same. So I just have to make the tops the same. I need this to equal this. Well, I've got a coefficient of x. This is 1x. That means I better make this equal to 1. A plus b has to equal 1. Likewise, this is all constant. There's no x associated with it. Negative a plus 2b, that has to equal 5. Okay. So one more time, I got all of this. I want it to be equal to this. The bottom's already the same. I need the top to be the same. So I have coefficient of x plus some mess equal to 1x plus 5. This coefficient behind my pen better equal 1. A plus b equals 1. And this stuff better equal 5. So there we go. A plus b equals 1. Negative a plus 2b equals 5. Okay. And from Algebra 1, we have a system of equations, right? 2 equations and 2 unknowns. And you could do that by substitution or by elimination, you might recall. In this case, it's easier to do elimination. If you add them up right away, the a's drop out. So 3b equals 6, which means b equals 2. Remember doing stuff like this in Algebra 1? Okay, then I just substitute back to find the value of a. Okay, so how about I plug back in here? If b is 2, you put a 2 right there, and a plus 2 equals 1. That means a is equal to negative 1. Okay, so that pretty much clinches it. Okay, so now that means x plus 5 over x plus 2, x minus 1. I have proven it's negative 1 over x plus 2 over x minus 1. And that is the same thing as what I have over here. I got them reversed, I guess, but they're the same thing, as you can see from here. Okay. All right, so this is called partial fractions. That's a technique of partial fractions. So now I'm going to do some problems that involve this thing of partial fractions. Okay. So my number 9. Again, my numbers don't exactly match yours necessarily, but nevertheless, you're still learning the material, hopefully, with that. All right, number 9 goes, let me just look at the book. Does it match? Yeah. 5x plus 1 over 2x plus 1, x minus 1. All right, so I'm going to try to force this thing to look like this. Once I make it look like this, then I'm good. Right? It's an easy integration. Some constant over 2x plus 1, some constant over x minus 1. Okay, right now ignore any symbols that I have there. All right, so notice this is first degree. The bottom is second degree. If you were to multiply all of that stuff out, it'd be second degree, right? Okay. If it wasn't, then you have to divide out first and do long division, and I'll show you that a little bit later. But that was sort of like the first one I did. That was like problem number 7. Right, number 7, you have to do some long division. Okay, so partial fractions. I will rewrite 5x plus 1 over 2x plus 1 times x minus 1 into a over 2x plus 1 plus b over x minus 1. Ignore this 1 and the 2 up above. That's actually going to turn out to be the answer, but pretend you don't know that yet. Okay, but if I can find a and b, it's a pretty simple integration, although you do have to watch out here by the chain rule. So there's a little bit of chain rule here. Somewhere I have to multiply by 1/2, it looks like, right? Because if I were differentiating, I'd multiply by 2. But anyway, we'll worry about that when we get to it. Okay, so just go ahead and write a over 2x plus 1 plus b over x minus 1. Find a and b. Okay, so a over 2x plus 1, b over x minus 1. And you know the way the game works. This side needs x minus 1 over x minus 1. This side needs 2x plus 1 over 2x plus 1. So there it is. You know, this side needs that, this side needs that. All right, so now I have a common denominator. 2x plus 1, x minus 1. Multiply out all the top stuff. So ax minus a plus 2bx plus b. So there it is, ax minus a, 2bx plus b. Then you group. Okay, put the x's together, put these two together. They both have x, right? If I factor out the x, it would be a plus 2b, correct? So a plus 2b x. These two do not have any x. They're going to be considered constant. So negative a plus b. Temporarily ignore that right there. Okay, so that is the same as that. You can double check, obviously, right? Multiply it back out. Ax, there it is, plus 2bx, there it is, minus a plus b, so it matches. All right, so here we are. Now I want you to look at this and this. So this whole thing and this whole thing. It's sort of just like what we did over here. Okay, we said that has to equal 1, that has to equal 5. Okay, so look at this and this. We want them to be equal. The denominators are already equal. So the top's going to be equal. This better be 5, and this better be 1, right? The top is 5x plus 1. 5x plus 1 over 2x plus 1, x minus 1. I want it to equal to blah, blah, blah over 2x plus 1, x minus 1. How am I going to accomplish that? I need this to be 5, right? If the top's going to match this, then I guess this coefficient better be 5 to match that, and this thing better be equal to 1. I mean, if it came out to be 2, they wouldn't match. If it came out to be negative 80, it wouldn't match. This thing better be a 5. This thing better be a 1. So then it would be 5x plus 1 on top. So there we go. I set a plus 2b equal to 5. I set negative a plus b equal to 1. So there it is. 2 equations and 2 unknowns. And then I just solve. Okay, so this is called partial fractions. We're going backwards from what we did in Algebra 1, right? Algebra 1, you did a lot of this. Combine, get a common denominator, blah, 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 comes out to be this. You probably didn't do too much of going backwards. Start with this. If you start with this, can you make it look like this? Okay, so that's the idea behind partial fractions. We're going backwards. All right. So in this case, again, it's easier to just add them up. So add them up. A's drop out. 3b equals 6. So b equals 2. And how about I put a 2 right back here? 2 times 2 is 4. So a plus 4 equals 5. That means a equals 1. Okay, so a is 1, b is 2. That's what I meant. Now going way back here, put a 1 here and a 2 here. And now it's very easy to integrate. I found the a and the b. So now this much harder integral, I can rewrite it like this. 1 over 2x plus 1 plus 2 over x minus 1 dx. Okay, both of these are natural log. This is just going to be 2 ln absolute value of x minus 1. This one's a little bit tricky because of the chain rule, because it's 2x plus 1. So I asked myself, if I were to differentiate at this stage, I would multiply by 2. Since I'm integrating, I multiply by a half instead. Okay, so it's going to be 1/2 ln absolute value of 2x plus 1 plus 2 ln absolute value of x minus 1 plus c. And that's my final answer. Okay, and notice again, it's an indefinite integral. So for indefinite integrals, that means there's no number here, no number here. Your answer is going to be blah, blah, blah plus c. Okay? Again, if you're not sure about this, what's the derivative of this? Okay, if I differentiate this, I would go 1/2, 1 over, right? To take the derivative of ln, it's 1 over 2x plus 1. Then by the chain rule, it's times 2 times the derivative of the inside. That 2 is going to knock out the half. So you get that perfectly. And yeah, the derivative of this is 2 times 1 over x minus 1, which is just that. Okay. So there we go. Okay, next one's a definite integral, problem 11. So let me show you 11. Bear with me just a moment. My bearings here. 2 over 2x squared plus 3x plus 1. Okay. I'm actually going to write this as 0x plus 2. And if you stop and think about how the other problems worked, it was a very similar fashion. So basically, if this is second degree, you want a first degree expression here. So if there's no x, just call it 0x. This is clearly the same thing, right? 0x plus 2 is the same as 2. And then I factorize the bottom. So this factors into 2x plus 1, x plus 1. That factorization should not be that hard. I mean, how do you get 1? The only way to get 1 is 1 times 1. And you know that a plus plus is a plus plus. So there we go. Okay, so I say to myself, 0x plus 2 over 2x plus 1, x plus 1. I want to break it into an a over 2x plus 1 plus b over x plus 1. Here's the answer. You're not supposed to see it yet. But do you agree, once I find a and b, the integration becomes easy, except right here, there's going to be a chain rule again. So I'm going to multiply by a half. Once again, well, it's just like this one here. All right, so I start off with this, a over 2x plus 1 plus b over x plus 1, like so. And now, once again, the left side needs the right side, and the right side needs the left side. So what do I need to multiply on the left side? X plus 1 over x plus 1. And what do I need to multiply on the right-hand side? 2x plus 1 over 2x plus 1. So now I have my common denominator, 2x plus 1, x plus 1. Here it is. Work out the top, ax plus a plus 2bx plus b. Right? Ax plus a, 2bx plus b. Group the x's together and the constants. Constants meaning they don't have any x. So these two are alike, right? So if I factor out the x, a plus 2bx, like that, plus parentheses, a plus b. Quick double check, multiply this out. Ax, there it is, plus 2bx, there it is, plus a plus b, plus a plus b. Okay, so we took inventory, so to speak, and it's all there. All right, and what do I want it to equal to? 0x plus 2. So 0x plus 2 over 2x plus 1, x plus 1. Okay, so I want this fraction to equal this fraction. Well, the bottom's already the same, so make the top the same. I need the coefficient of x to be the same. In other words, this is 0. So a plus 2b is equal to 0. And then I need the constants to match. I need this stuff here to be 2. I mean, if this came out to be 3, it wouldn't be true. If it came out to be 1, it wouldn't be true. I need it to be equal to 2. So my two equations and two unknowns are a plus 2b equals 0 and a plus b equals 2. So two equations and two unknowns, very easy. Okay, in this particular case, it's easier to subtract. Okay, I subtract because a minus a is 0, right? 2b minus b is b. 0 minus 2 is negative 2. So that means b is negative 2. Plug back in, a is 4. And then I just say, etc. You can finish the rest of the problem very easily, but that's that. So put negative 2 right here. So a minus 2 equals 2, add 2, a equals 4. Okay, so you're just integrating 4 over 2x plus 1 minus 2 over x plus 1, and I'll just say etc. for the rest of that one. Okay. All right, so that's the first few examples. The next one is going to be much, much longer and much more difficult, unfortunately. Okay, so let me make this disappear. I've reached the bottom of the paper. Okay, so next one I want to show you is 17. So I went a little out of order here. Let me check if that's the same as, yeah, it's the same. This one is much longer. Okay, 4y squared minus 7y minus 12 over y times y plus 2y minus 3. Really, really long. Okay. So quick check. This is third degree. If you multiply all the bottom out, you have a y. There's y cubed and other stuff. And this is y squared. So that's okay. Right? In the proper form, the degree of the denominator is greater than the degree of the numerator. And if it isn't, let's say this was fourth degree, and this is third degree, you would do polynomial long division. But we don't have to here. And you should know it doesn't matter if you have y or x or whatever. Okay, so 4y squared minus 7y minus 12 over y times y plus 2y minus 3. This time I break it down into this. A over y plus b over y plus 2 plus c over y minus 3. Ignore this for the moment. And now I have to find a, b, and c. Okay. That's going to be a lot more work. But I do want to say this. Once you can find a, b, and c, it's a very easy integral. They're all ln's. Right? So pretend this came out to be, I don't know, 5, and that's negative 21, and that's 17. It's just going to be 5 ln absolute that, right? And whatever I said, negative 21 ln absolute that, plus whatever that is, ln absolute y minus 3 plus c. Okay, so if you can temporarily ignore the red, ignore all the red, a over y, there it is, b over y squared, b over y plus 2, c over y minus 3. This time to get a common denominator, you can see there's a lot more work. Now, if we only had two things like this, you know what to do. You just say, oh yeah, this one needs y plus 2 over y plus 2. This one needs y over y. What happens if I have 3 of them? Well, to get a common denominator, in this case, the common denominator is all 3 of them, y plus 2, y minus 3. So each of these fractions needs 2 things. Is that right? So what does the first fraction need? It needs these 2 guys. So y plus 2, y minus 3 over y plus 2, y minus 3. If you can't read that, you just say, what does this need, right? This needs y plus 2 over y plus 2, y minus 3, y minus 3. What does the middle one need? Well, the middle one needs these 2. So y minus 3, y minus 3. And what does the last one need? Last one needs these 2. So y plus 2, y plus 2. So now all 3 fractions have a common denominator. Y plus 2, y minus 3. They all have all 3 of them, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, in some order. Okay. The messy part is figuring out the top. Okay, so it's A, y plus 2, y minus 3. B, y minus 3. C, y plus 2. All right, that's a lot. I decided not to do the A, B, and C. I'm just going to distribute the stuff in red. Okay, so leave the A alone. Okay, y plus 2, y minus 3. You can follow that out as well as I can. Y squared minus y minus 6. Okay, y squared minus 3y plus 2y is minus y minus 6. And these aren't too bad. Y squared minus 3y. And y squared plus 2y. Okay, there it is. So now I'm at this stage. Now, if you were my Algebra 1 students, I would multiply this all out. I'm not going to do it. I'll just say it maybe. You know, ay squared minus ay minus 6a plus by squared minus 3by plus cy squared plus 2cy, right? And the combined like terms. However, I'm trusting the fact that you're Calculus 2 students. You're all good at algebra. You can follow along the logic. Okay. Rather than doing all that, you know that I want to group it as y squared, y, and constant. Constant means there's no y. Okay. So I trust you can see what I'm doing. I want to combine all the y squareds. There's an ay squared, by squared, cy squared. So a plus b plus c. So that prevents us from having to write that long thing out that I just said, right? ay squared minus ay minus, that whole thing, which I would do if you were my Algebra 1 students, but your algebra is good. I think you can follow along. You can look at this and say, oh yeah, ay squared plus by squared plus cy squared. There it is. It's a plus b plus cy squared. Okay. I'm going to do the same thing for y. Okay, let's see. Take a look at these two. Negative ay, correct? So negative a, here's the y. Right here, there's y. Negative 3by, agreed? Negative 3by, there's a negative 3b, I factored out the y. And right here, 2cy, 2c. So parentheses y. And then constant, it looks like there's only one constant, negative 6a, which is right here, a times negative 6. And there's no other constant. Well, we can also take inventory. There's 1, 2, 3, 4, 5, 6, 7 terms. So this should have 1, 2, 3, 4, 5, 6, 7. Yeah, so that matches. All right, there we go. This big mess, a plus b plus c, y squared, plus, parentheses, negative a minus 3b plus 2c times y, plus a negative 6a, all over y plus 2, y minus 3. It has to equal this thing. Okay? Which means, take a look, we already have the bottom matching, so I need the top to match. Well, if this is going to match this, the coefficient of y squared has to match, the coefficients of y have to match, and the constants have to match. So that means this a plus b plus c better be equal to 4. So there it is, a plus b plus c equals 4. This stuff, negative a minus 3b plus 2c, better be equal to negative 7, right? They're both the coefficient of y. And then the constant here means there's no y, negative 12, better match negative 6a. So this time I have 3 equations in 3 unknowns. Right, so the ones we did before were 2 equations, 2 unknowns. This is 3 equations, 3 unknowns. Okay? If I had 4 things here, and I won't give anything that bad, at least not to work out the whole thing. But let's say you had y plus 2, y minus 3, and y plus 5. You'd have 4 equations and 4 unknowns. And you can have as many as you want, 5 equations and 5 unknowns, 10 equations and 10 unknowns. But, I won't torture you with anything that bad. I mean, this itself is already quite a bit of torture, so to speak. Okay. So we solved 3 equations, 3 unknowns. Fortunately, that last one is very easy. A is 2, right? So put a 2 right there. If I subtract 2, it looks like this. B plus C equals 2. Put a 2 right there. That would be a negative 2, right? So to get rid of the negative 2, I would add 2. If I add 2, that becomes a negative 5. Okay, so right now I have 2 equations and 2 unknowns. B plus C equals 2. Negative 3b plus 2c equals negative 5. Okay, so you know this trick from algebra, right? Multiply both sides of the top equation by 3. That way this is a 3b, this is a negative 3b, so when I add them, they cancel out, right? So if I multiply this equation by 3, it looks like this. 3b plus 3c equals 6. And now I can add these 2 equations. So the b's drop out. 5c equals 1. So c is a fraction 1/5. We're stuck with it. But that's okay. Not really that big a deal. And so c is 1/5. Plug back in here. b plus 1/5 equals 2. So I subtract 1/5. 2 minus 1/5. 2 minus 1/5 is 9/5. So I have A, B, and C. Plug them way back here, A, B, and C. 2, 9/5, 1/5. You say, this doesn't come out nice. It doesn't matter. I don't care if this came out to be pi over square root of 3 or whatever. It's a constant. You just put that constant and then ln. All right, so here we go. The problem ends up looking like this. And then I'm going to say, etc. So the original